Have you ever wondered about mass and weight? We use the words interchangeably all the time, but in physics, they are totally different things. So, what's the real story? Well, in this explainer, we're going to settle that question once and for all by taking a little trip to the moon. Let's dive in.
Okay, so here's the big puzzle that gets this whole thing started. Imagine you could step on a bathroom scale on the surface of the moon. The number it would show you would be way, way less than what it says here on Earth. But you haven't changed, have you? You're still made of the exact same amount of stuff. So what's going on? That is the mystery we are here to solve.
And here's our roadmap. We're going to take this step by step. First, we'll nail down exactly what mass is. Then, we'll do the same for weight. We'll put them head to head to see the differences, and then we'll actually do the math for your weight on the moon. That'll lead us to the big finale, understanding your constant self.
All right, first things first. Let's talk about mass. I want you to think of mass as your constant foundation. This is the part of you that does not change no matter where you go in the entire universe.
So, what is it exactly? Well, the textbook definition is pretty simple. Mass, and in physics, we almost always write this with a lowercase m, is simply the quantity of matter in an object. It's the grand total of all the atoms, all the particles, all the stuff that makes you up.
Now, mass has some really specific properties. First, it's what we call a scalar quantity. That just means it's a number, a magnitude, and that's it. It doesn't have a direction. Second, and this is the big one, it's constant everywhere. Your mass is the same on Earth, on the moon, or floating in deep space. Its official SI unit is the kilogram, or kg. Mass is also a measure of inertia, which is basically how resistant an object is to being pushed around. And finally, if something physically exists, it has mass. It can never be zero.
Okay, we've got mass down. Let's move on to the other side of the coin, weight. Now, if mass is the stuff you're made of, weight is a completely different beast. It's not about the stuff itself, it's about a force acting on that stuff, specifically the force of gravity. So here's the formal definition. Weight, which we represent with a capital W, is the force of gravitational attraction between an object and a planet. It's the pull that planet exerts on you, trying to draw you toward its center. Now, to understand how we calculate weight, we need to pull out one of the absolute cornerstones of physics, Sir Isaac Newton's second law of motion. It states that force equals mass times acceleration. F equals m times a. This is the fundamental rule for what it takes to get an object to change its motion.
And here's the connection. When we're talking about the force of weight on a planet, the acceleration isn't just any old acceleration, A. It's a very specific one, the acceleration caused by that planet's gravity. And because it's so special, we give it its own symbol, a lowercase g. So we can just swap out the A for a G.
And there we have it. The moment we substitute g into the equation, the general concept of force becomes the very specific force we call weight. So the formula for weight is beautifully simple. Weight equals mass times the acceleration due to gravity. W equals m times g.
So let's look at the properties of weight, and you'll see how different they are from mass. First, weight is a vector. This means it has both a number, or magnitude, and a direction. That direction is always pulling you down toward the center of the planet. Because it depends on g, weight is variable. It changes depending on which planet you're on. The SI unit for weight isn't the kilogram, it's the Newton, represented by a capital N. And crucially, unlike mass, your weight can be zero if you're far enough from any source of gravity.
Okay, we've defined mass, we've defined weight. Now it's time for the main event. Let's put them side by side for a direct showdown to make sure the difference is crystal clear. This table really says it all, doesn't it? Mass is the amount of stuff. Weight is the pull on that stuff. Mass is constant. Weight changes with location.
The unit for mass is the kilogram. For weight, it's the newton. Mass is just a number. Weight has a direction. Mass can't be zero. Weight can. They really are two fundamentally different concepts.
So now that we have all the theory locked in, we can finally go back to our original question. It's time to apply what we've learned and calculate exactly what your weight would be on the moon.
All right, to do this right, we need to use the full formula from Newton's universal law of gravitation. It looks a little scary, but let's just walk through it. Your weight on the moon, which we'll call W subscript m, is equal to a special number g, the gravitational constant, times your mass m, times the mass of the moon, m subscript m. All of that is then divided by the radius of the moon, r subscript m, squared.
And we can write the exact same formula for your weight here on Earth, or W subscript e. The formula has the same structure. G is the same, and your mass m is the same. The only things that change are the planet's mass, which is now a capital M for Earth, and the planet's radius, a capital R for Earth.
Now for the really cool part. We have our two big equations, and we have all the data we need. It's time to put it all together and finally calculate the difference. And here are the numbers we're going to use. Just take a second to look at the scale here. The mass of the Earth is more than 80 times the mass of the moon. These huge differences in mass and radius are the entire reason your weight changes.
Okay, now here's a clever little math trick. Instead of calculating both weights and then comparing, we can just divide the moon weight equation by the Earth weight equation. And when we do that, the gravitational constant g on the top and bottom cancels out. And even better, your own mass m also cancels out. This leaves us with a much cleaner formula that only involves the masses and radii of the Earth and Moon. So now, we just take those big numbers from our data table and we plug them directly into our new ratio formula. The mass of the Moon times the radius of the Earth squared, divided by the mass of the Earth times the radius of the Moon squared.
You run all those numbers through a calculator, and after all that complex physics, what you get is a beautifully simple result. Approximately 1/6. And that's it. Your weight on the moon is just 1/6 of your weight here on Earth. Mystery solved.
So we've followed the definitions, we've done the math, and we've found our answer. Let's just take a moment to wrap this all up and focus on the single most important idea from this whole explainer. And here it is. Your mass, the actual quantity of matter that makes you, never changes. It's constant. Your weight, on the other hand, is just a temporary measurement. It's the force of gravity at your current location pulling on that constant mass. The moon is much smaller than the Earth, so its gravitational pull is weaker. Simple as that.
Which leaves us with a final thought to ponder. If your weight is just a local force, what do you think would happen if you were floating in deep space, millions of miles from any planet or star? Your mass would still be the same, but what would your weight be? Something to think about. Thanks for watching.